Welcome to Connecting the Dots, the channel where we try to predict where disruptions will take us. In its recent Investors Day, Tesla declared its intent to produce a permanent magnet motor that doesn't require any rare earth elements. To understand how Tesla will do this, in this video, we'll dive deep into the technology behind this development. First, we will provide the problem by examining different types of electric motors and discussing their respective pros and cons. Then, we will provide a basis for understanding how the problem can be solved, by explaining the physics behind magnetism and how permanent magnets are made. With these in mind, we will then dive into potential methods for eliminating the use of rare earth elements. We'll discuss companies involved in the field and review ongoing research. Finally, we will summarize what we have learned and try to assess which approach or what companies Tesla might be using to achieve this feat. And I respect your time, so section markers are provided for all sections. If you like my videos, please like and subscribe to help this video reach more people. A special thank you to my Patreon supporters and YouTube members. Your support is what gives me the freedom to do deep dives like this and like my Highland videos. If you want to support the channel, there's a link in the description. Before going on, here's a game for you. In this video, I hit a reference to a prominent member of a Tesla Twitter community. The first person to post a timestamp to it in the comments will win a mug of their choice from my newly updated merch store. Link in the description. And now, buckle up and get ready, because we're about to dive into brand new disruptive technologies. And disruptions are never boring. Electric motor types. To fully appreciate the significance of Tesla's announcement, we first need to understand the two primary types of electric motors used in electric vehicles: permanent magnet, or PM, motors, and induction motors. Understanding the distinct characteristics and advantages of each type is important for the rest of the video, but since many of you know this already, I'll be brief. Motors usually consist of a stationary part called stator, and a smaller part rotating within it called rotor. Magnetic fields acting between the stator and the rotor create attracting or repelling forces which push or pull the rotor, and the torque these forces produce around its axle causes the rotor to rotate. This rotation can then be harnessed to power devices such as electric vehicles. So motor operation all begins with magnetic fields. But how are these magnetic fields generated?
The coils of the stator, that is, the stationary part, are powered by a three-phase electric power of alternating current. In this way, they produce a rotating magnetic field that rotates a fixed speed related to the power frequency. The rotor can be made with permanent magnets. The opposite poles of the stator and rotor attract each other in such a way that the magnetic field of the stator rotates and attracts the rotor, forcing it to rotate at the same speed.
As their name implies, permanent magnet, or PM, motors utilize permanent magnets to generate the magnetic field necessary for their operation. These magnets are typically made from rare earth elements like neodymium, terbium, and dysprosium, which are known for their strong and consistent magnetic properties. Instead of using permanent magnets, induction motors generate their magnetic field by inducing a current in the rotor.
The stator is basically a three-coil winding powered by three-phase alternating current. The flow of a three-phase current through these windings causes the formation of a rotating magnetic field. It is precisely this rotating magnetic field that causes the rotation of the rotor. If we apply a three-phase electric power to this coil arrangement, the magnetic field will be generated at a specific moment. Following the variations of the alternating current as shown, the magnetic field will assume different orientations and form. When we compare these three results, we can see that it is like the rotation sequences of a magnetic field of uniform strength. Let's try now to place a closed conductor inside the rotating magnetic field. Since there is a variable electromagnetic field in a closed circuit, an induced current will be created on the conductor. We can therefore say that the rotating magnetic field will induce a current in the loop.
Induction motors have been around since the late 19th century, when they were invented by no other than Nikola Tesla. For a long time, these motors were limited in their performance, because it was difficult to control the rotation of the current through the stator windings. However, in the past decade, advances in microprocessor control technologies have solved many of these problems. Tesla uses PM motors to power both front and rear wheels of models S and X, and the rear wheels of models 3 and Y. For powering the front wheels of all-wheel drive models 3 and Y, however, they use an induction motor. PM motors are preferred as they're more efficient and have higher power density than induction motors, which enables EVs to get more range and better performance from a smaller, lighter, and easier to integrate package. The reliance on permanent magnets has several drawbacks, however. The first of which is cost. With EV production growing exponentially in the last few years, permanent magnet prices have sharply increased. Another drawback is that mining and production of rare earth elements is not eco-friendly. And most importantly, while 90% of EVs globally use PM motors for propulsion, China presently supplies 91% of the rare earth oxides from which magnet materials are obtained. This puts China in a position where they can completely halt EV production in the West in case trade relations go sour. Creating permanent magnet motors without rare earth elements will enable Tesla's Gen 3 platform to use motors that are light, power dense, and efficient, but also inexpensive to make and less reliant on price fluctuations and supply chain issues. Clearly, this is desirable. But how can they achieve it? To answer that, we first need to delve into the science behind magnetism and understand why rare earth elements have become such a critical component in permanent magnet motors. 2. Making a magnet. We all know what a magnet is, but how is magnetic force created, and what makes rare earth elements suitable for strong and long-lasting magnets? To answer this, imagine that we are tasked with creating a permanent magnet. Where do we start? Magnetism starts with the spin of electrons around individual atoms, so let's start there. Only some kinds of atoms have what physicists call a magnetic moment, which means that each atom acts like a tiny bar magnet with a north pole and a south pole. So let's focus on atoms that are strongly magnetic, such as iron, nickel, and cobalt, or rare earth elements such as neodymium. But having atoms that act like bar magnets isn't enough, because the way these atoms are arranged is also important. If bar magnets are aligned the same way, they attract each other, and together they act as one larger and stronger magnet. While if they face in opposite directions, they repel each other and cancel each other's magnetic field. So, we'll need a material in which these atomic bar magnets naturally tend to line up. This happens in many crystalline substances because of something physicists call exchange forces, a quantum mechanical effect that operates over just a few nanometers, coaxing the magnetic moments of nearby atoms to align. In many materials, that alignment is easily disturbed, destroying the magnetization. To avoid that, it's best to pick a material whose crystal lattice has a single direction in which the magnetization can align with, somewhat like a grain in a piece of lumber, or how water flows in a pipe. This direction is called the easy direction of magnetization, and since atoms in such materials prefer to align in that orientation, this makes for a stable magnet. We now have a crystal where the atomic bar magnets are aligned. But it doesn't end there, because most crystalline materials actually consist of many small separate crystals, with each crystal's easy direction pointing in a random direction, and just like with atoms, if these crystals are not aligned with each other, they will cancel each other's magnetic field, and we won't have a magnet. The solution to this is to work hard to align the easy directions of all the crystallites in parallel. Don't worry, we're almost done, just not yet, because even if all crystals point the same way, let's say in the right-left direction, in some crystals the atoms will align so that north is left and south is right, while in other crystals the atoms will align the opposite way. This will divide our material into what are known as magnetic domains, where each domain acts like a bar magnet, but just like we saw with misaligned atoms, misaligned domains cancel each other's field. This is easily solvable by using brute force. Applying a strong magnetic field with a powerful electromagnet will gradually force the atoms in all domains to point the same way. At this stage, the entire lump acts as a single large magnet, and a good permanent magnet will keep most of that magnetization after the applied field is removed. I described this stage as brute force because we really want to use materials in which this stage is hard to achieve. If a relatively weak magnetic force was enough for us to realign the atoms, then this magnet won't be useful for us in EVs. Magnets work in a hostile magnetic environment, which tries to demagnetize them. So if a weak force is enough for that, that magnet will not be useful. If, however, a whole lot of effort is required to realign the atoms, this means the magnet will be stable even when used in a motor. The strength of the magnet when all atoms are aligned is called saturation magnetization. And the strength of magnetic field required to erase magnetization is called coercive field. And here's where it gets interesting, because materials with high saturation magnetization usually have modest coercive fields, and vice versa. So are we doomed to choose between strong magnets, which will get demagnetized while used in a motor, or stable magnets, which will stay magnetized but will produce low power right from the start? Obviously not. And the key to solving this is that so far we only discussed atoms of a single element, but by mixing and matching particles of different elements and applying heat and pressure to create alloys or nanocomposites of them, we can create magnets which combine one element's saturation with the other's coercive field. Now that we know how magnets are made, we need to add one final factor before going on to tackling alternatives to rare earth materials, which is the Curie temperature, named after the famous physicist Marie Curie. The Curie temperature is the point at which a magnetic material loses its magnetism due to thermal energy disrupting the aligned magnetic fields of its electrons. For a magnet to be effective and long-lasting, it must have a high Curie temperature, ensuring that it retains its magnetic properties even under when the motor gets hot. Magnets combining rare earth elements such as neodymium iron-boron alloys are particularly effective at creating strong magnets because they combine the rare earth element's strong magnetic properties with the regular metal's magnetic stability. For these reasons, all permanent magnet motors used in EVs currently use rare earth elements. If you're watching this video, chances are that, like me, you love engineering and sciences and generally love learning. But if you really want to understand topics like electricity and magnetism or neural networks, then it isn't enough to just passively watch a video, because learning is easier and deeper when you actively engage with the material. Brilliant.org, the sponsor of this video, is a great place for that. Brilliant offers thousands of lessons, from foundational and advanced math to AI, neural networks, and more. New lessons are added monthly, and they even offer scientific thinking and everyday physics courses to help hone your first principles thinking skills. Touching with the topic of this video, they even have a great course on electricity and magnetism, which methodically progresses to E&M with questions, simulations, videos, and experiments. I think this is the best way to learn because the sequence of steps is extremely well thought out. Each lesson builds on the previous, with a gradually increasing level of difficulty. Each step contains questions you need to answer, which forces you to check your understanding and helps cement your knowledge. And whenever you need help, you'll find useful explanations or hints. As someone who's interested not just in learning but also in teaching methods, I was impressed by the level of interactivity Brilliant provides. This helps you learn everything from statistics to machine learning in a very active, fun way. So I encourage you to go learn new skills while having fun by signing up to Brilliant with my link in the description. Brilliant.org/CTDots. Brilliant are offering 20% off the annual premium subscription to the first 200 people who sign up, and you'll have a 30-day trial, so you have nothing to lose. So head off to Brilliant and experience it for yourself. And thank you, Brilliant, for sponsoring this video. 3. Eliminating rare earth elements. As we previously saw, using rare earth-based permanent magnets in motors has several disadvantages, mainly increasing costs and adding yet another dependency on China. So how can Tesla eliminate them? One approach is to ditch permanent magnets altogether and use induction motors, like Tesla does for the front wheels of Models 3 and Y. This approach is now taken by companies such as Renault, who have made a strategic decision to shift towards induction motors for all their electric vehicles. Induction motors are inherently efficient at high revs, and recent advances, such as increased control software and using insulators instead of air in parts of the rotor, considerably improves efficiency in low revs and make them more of a viable option. However, PM motors still lead in efficiency and energy density, and Tesla said that they will use permanent magnets, just without rare earth elements. So let's explore these options instead. A. Using rare extraterrestrial elements. The first way to eliminate rare earth materials is to replace them with rare extraterrestrial materials. You might think I'm joking, but I'm seriously suggesting that Tesla might use materials that originated from outer space. Specifically, we're going to look at tetratanite, a rare meteoritic metal, and explore its potential as an alternative to rare earth elements in permanent magnet motors. The mineral taenite is an alloy of iron and nickel with a chemical formula of FeNi, which is found on Earth mostly in iron meteorites. Tetratanite is a tetragonal crystalline form of taenite, which gives it the chemical formula of L10FeNi, which from now on I'll refer to as L10. It's made up of stacked layers of iron and nickel in an ordered crystal structure, which is arranged in a specific pattern that gives it unique magnetic properties. In fact, tetratanite has an intrinsic magnetic strength that rivals that of the strongest permanent magnets known to humankind, like neodymium magnets. The reason that tetratanite is only found in meteorites is that its ordered structure cannot form under oxidizing conditions, such as Earth's atmosphere. Tetratanite is formed over millions of years, when meteorites containing iron and nickel cool down at an incredibly slow rate. This process allows the atoms to arrange themselves into the specified ordered structure responsible for its remarkable magnetic strength. You might be wondering how we could possibly use such a rare extraterrestrial element in large-scale production. The answer is that researchers have been investigating ways to replicate the formation of tetrataenite under controlled conditions here on Earth. In the 1960s, tetrataenite was artificially formed by blasting iron-nickel alloys with neutrons, which allowed the atoms to form the desired ordered stacking. This process is expensive and non-scalable, so it's an extreme example of prototypes are easy, production is hard. A cheaper and more scalable way has to be found. But how do we get there? As previously said, tetrataenite is an alloy of iron and nickel, so the process starts with melting these two metals together. This part is easy, but the real problem is finding a way to cool the molten metals while getting the nickel and iron atoms to arrange in the desired L10 crystalline manner. There are 3 ways to achieve this, but considering Tesla's ambitious timelines, let's drop the first way, which is to cool the mixture down over millions of years, and head to the 2 practical solutions, one developed in the USA and the other in Europe. The first method, developed by researchers from Northeastern University led by Professor Laura Lewis, is described in U.S. Patent Number 11462-358. This method is performed as follows. First, iron, nickel, and one or more elements from the list shown on the screen are melted together. The melt is then cooled to create a solid iron-nickel alloy. When the solid is below the chemical ordering temperature of L10 tetrataenite, pressure is exerted to it to create a plastic deformation in a longitudinal direction. The solid is then pulled at the longitudinal direction to form extensional stress, and a magnetic field is then applied along that direction. Then, in a reduced oxygen environment, the solid is heated again to a temperature which is higher than the chemical ordering temperature of K10 tetrataenite. Finally, the solid is cooled to a temperature which is lower than the chemical ordering temperature of tetrataenite, and at this stage the magnetic FeNi alloy material containing L10 ordered structure is obtained. Overall, the process is pretty simple. Just heat, cool, press, pull, magnetize, heat and cool again, and you have tetrataenite. But the devil is in the details, and the process still requires optimizing. The second method was developed by researchers from Cambridge University, the Austrian Academy of Sciences, and the Montan-Universität in Leoben, led by Professor Lindsay Greer. The team studied the mechanical properties of iron-nickel alloys containing small amounts of phosphorus, an element that is also present in meteorites. The pattern of phases inside these materials showed tree-like growth structures called dendrites. This was expected, but the team discovered that the dendrites have a peculiar diffraction pattern which suggests an orderly structure. A closer look revealed that these dendrites were tetrataenite. In this picture, we see a rod and a button, cast of an iron, nickel, phosphorus, and carbon alloy. Checking the rod with a scanning electron microscope reveals tetrataenite dendrites made of ordered iron and nickel in a carbon and phosphorus matrix. These pictures show results with different ratios of iron, nickel, phosphorus, and carbon. In all cases, electron diffraction shows that the dendrites are indeed L10 ordered tetrataenite. It appears that phosphorus, which is also present in meteorites, allows the iron and nickel atoms to move faster, enabling them to form the necessary ordered stacking without waiting for millions of years. By mixing iron, nickel, and phosphorus in the right quantities, they were able to speed up tetrataenite formation by between 11 and 15 orders of magnitude, such that it forms over a few seconds in simple casting. What's most astonishing is that no special treatment was needed. The entire process consists of melting the alloy, pouring it into a mold in the shape of the desired magnet, and in a few seconds, you have L10 tetrataenite. It doesn't get simpler than this. However, just like with Northeastern, this method isn't fully optimized yet either. The exact ratios of all 4 ingredients have to be optimized, and the resultant magnets need to be tested in engines. To sum this part up, while both methods seem very promising, they still have a way to go before they're ready for mass production and use in high-performance EV engines.
The challenge is getting that material from the laboratory, from the small quantities that we can make, into a form that can be put into something like a motor or generator. There's chemistry that's involved, there's mechanical engineering, there's electrical engineering. All of these disciplines have to come together in order to produce the technology needed to manufacture this material.
When discussing how tetrataenite was first produced by bombing with neutrons, I quoted Elon Musk's, "Prototypes are easy, production is hard." So although the new methods seem much more viable, they still have a way to go before being ready for prime time. But if and when they materialize, the significance of this will be immense. B. Using earthly metals. If Tesla can make tetrataenite, then it's game over. It doesn't get better than that. But assuming it can't, let's explore other alternatives to rare earth metals. The following table compares the most common metals currently used for magnets. The first line shows neodymium-based magnets as a reference for comparing the other metals. The other two lines show alnico, or aluminum nickel cobalt magnets, and ferrite magnets, made of ceramic materials and iron oxide, which is a fancy way to say rust. Looking at the maximum energy product, we see that at 25 to 55 MGOE, neodymium trumps alnico's 1 to 11 and ferrite's 1 to 5. This means that rare earth-free motors using alnico, and especially ferrite magnets, would either lack power or be much larger and heavier than a neodymium-based motor. As for coercivity, both other metals are much more less resistant to demagnetization than neodymium magnets. Both alnico and ferrite magnets have a cost advantage over neodymium magnets. Before going on, let's drop alnico. Although widely used for permanent magnets, their advantages over ferrite are not enough to overcome their increased price, and especially their dependency on cobalt. If there was no other way, then sure, Tesla could consider it. But if ferrite magnets are enough, then I really don't see Tesla committing to increase their use of cobalt in upcoming years. But are ferrite magnets enough? The digital and AI revolutions enabled much better optimization of motors in the design stage, as well as controlling their operation in a level of precision that was simply impossible before. So although motors are mature, last December, Hitachi Motors, now renamed Proterial, announced that they have verified that by optimizing motor design, they were able to achieve with ferrite magnets the same level of performance as with neodymium magnets. They still need to either grow engine weight by 30% or increase its RPM, but both options are definitely viable. So ferrite magnets-based motors are possible. Let's go on to newer metals. Niren Magnetics, a spin-off of the University of Minnesota, developed a new type of magnet material based on iron nitride. The proprietary process involves nitrating iron in a way that turns it, you guessed it, into an ordered crystalline structure which has extremely strong magnetic properties. The crystal form of iron nitride was discovered in 1951, and its magnetic properties were explored in the early 1970s and again in the 1990s. But this metal was difficult to work with and results weren't easily reproducible. So interest in it waned until the late 2000s, when methods of producing thin films of the material were developed. Using thin films of this material, such as Niren's process produces, enables magnets 3 times as powerful as neodymium magnets at much lower cost, and without all the environmental and supply chain issues that rare earth elements have. This enables making powerful, lightweight, and compact motors. Shortly after Investor Day, 2-Bit DaVinci released an excellent video in which they presented Niren and their magnets. I fully recommend watching that video for the technology, but I'm afraid that Tesla has nothing to do with Niren and its invention. When questioned about Tesla's announcement, Niren Magnetics CEO Andy Blackburn said that you get a new commercial magnet a couple times a century. He expressed disbelief that Tesla had invented a fundamentally new magnet material and believes that Tesla had decided it can make do with a much less powerful magnet such as ferrite. In other words, Tesla's not in cahoots with Niren, so let's go on. C. Coatings and nanocomposites. Until now, we've discussed metals, or rather alloys, used for magnets. But there are other levers which Tesla could pull, one of which is magnet production method. One such option is coatings. Magnets are often coated with protective layers designed to protect them from corrosion. But in this case, I'm referring to coating a magnet core, made from one magnetic material with a thin layer made of another magnetic metal. If one has strong coercivity, while the other has strong magnetic strength, this enables forming a magnet which is both stable and powerful. Another option is to use nanocomposites. The process we previously described in the magnetism chapter, where 2 magnetic metals were heated and pressed together, is fairly new. Done right, it too can combine the coercivity of one material with the magnetic force of the other. On top of everything we saw, there's another option in which Tesla proves the experts wrong yet again by inventing a whole new magnetic material. In fact, I originally planned to make the entire video on research directions in which Tesla could approach this topic. For example, they could use the latest AI methods to find novel ways of creating magnetic matter. They could also bring magnetic metals to the Curie temperature and see how demagnetization occurs, and then try to reverse engineer a backwards-going process. There are several such options, but the video is long as it is, so let's focus on what we already know. So what will Tesla use? It's extremely important for Tesla to create a motor that is powerful enough, yet compact and light, because although the Gen 3 car doesn't need flat acceleration, a heavy engine costs range, and a larger one could pose packaging concerns. In addition, since the engine also works on regen, it has to be powerful enough to capture the car's energy without forcing the driver to use the brakes and lose range. Nobody outside of Tesla has an idea what exactly Tesla will do, but we can assign probabilities to the different options. So there's a high probability that Tesla will use ferrite magnets. It's also highly probable that they'll use a ferrite core with a different coating. There's even a small chance of an iron core with coating. It is possible that they will use nanocomposite magnets. It is somewhat possible that they'll use tetratenite. Logic dictates that the probability of this is small, as all methods for producing such magnets are still at lab scale and production's really hard. However, Tesla's pace of innovation is like no other company, and they are known for achieving breakthroughs much faster than others can. So for wishful thinking alone, I'm not ruling out this option. And there's a very small chance that they're using iron nitride magnets developed with or without iron. Time will tell, but tetratenite or not, I think we can all agree that Tesla's technology is out of this world. Let me know what you think on which magnets Tesla will use. Also, let me know if you'd like to see more videos diving deep into technology like this one. In a few seconds, I'll show a poem written by GPT-4 to hail Tesla for their achievement. But first, reminding you that the first viewer to post a timestamp to where I hit a reference to someone from the Tesla community will get a free mug of their choice from my newly launched merch store, link in the description. My next video will dive into one of Tesla's critical supply chains. And if you liked this video, please consider supporting me on Patreon or as a YouTube member. A super thank you for the super thanks to Jeffrey O, and to my latest patrons, Michael G, Carla A.M., Michael M, and Brent. And to all my patrons, you guys rock. And now, as promised, here's The Magnetic Dance of Change by GPT-4. In a world of boundless marvels, where the seeds of change are sown, rises Tesla, proud and dauntless, champion of a dream unknown. With a mission, firm and focused, Tesla strives to pave the way for a world that's clean and thriving, where sustainable energy holds sway. Magnetic force, both pure and thrifty, shatters chains of days gone by. Tesla's gift, a future gleaming, where the dreams of all can fly. In the workshop of the wise ones, minds of genius toiled and wrought, a motor clean for every people, a revolution's dawn now brought. Tesla's gift, a promise soaring to empower Earth's many souls, a sustainable solution in the hands of rich and poor. Celebrate the tale of Tesla in the annals of our race, their legacy a world united, a beacon bright forever traced. Guided by the Muskian vision to a future we all share, Tesla's mission, our great rebirth, sustainable energy everywhere.